Let's do a quick recap of pH and solubility of salts with a real-life example that will help you remember it better. Ammonium chloride. When ammonium chloride dissolves in water, it splits into ammonium ions, that's NH4+, and chloride ions, Cl-. The chloride ion is a spectator ion. It doesn't react much with water and just hangs out. But ammonium ion is special. It's the conjugate acid of ammonia, a weak base. So ammonium ion can donate a proton, H+ ion, to water, making the solution slightly acidic. This reaction can be represented as an equilibrium between ammonium ions in water and ammonia plus hydronium ions. Here's where pH comes into play. If you make the solution more basic, that is, increase the pH, you reduce hydronium ions. Le Châtelier's principle tells us the system will try to balance by shifting that reaction to produce more hydronium ions. That uses up ammonium ions. As a result, more solid ammonium chloride dissolves to replace those ammonium ions, so solubility goes up in basic conditions. On the other hand, if you lower the pH by adding acid, you increase hydronium ions. The reaction shifts the other way, producing more ammonium ions from ammonia. This means fewer ammonium ions need to come from solid ammonium chloride, so its solubility decreases. In short, ammonium chloride is more soluble in basic solutions. It's less soluble in acidic solutions. This concept isn't just theoretical, it's vital in agriculture where ammonium chloride fertilizer's solubility depends on soil pH. Farmers use this to ensure plants get enough nitrogen from ammonium ions. In summary, to determine whether a salt is more soluble in acidic or basic conditions, ask yourself, do any of the ions undergo hydrolysis? If they do, apply Le Châtelier's principle to analyze how changes in pH will shift the equilibrium, either producing more ions or fewer, which in turn affects solubility. If the salt is neutral and its ions do not undergo hydrolysis, then its solubility is largely unaffected by the pH of the solution.